For this next example here, we're going to be trying to solve for x, but this time instead of x being our exponent, it's going to be our base value. To solve for x here, what you want to do is try to isolate it as best as you can. My strategy for this one is to rewrite this fractional exponent as a radical. There we go. And from here, I can slowly just reverse out everything that I see. So the first thing I see is that radical 3, I'm going to reverse that out by cubing everything. So if I cube the left, if I cube the right side there, if I cube everything, on the left side I'm only left with x exponent 4. This is now equal to 16 cubed, which is 4096. From here, I'm going to cube root both sides, or sorry, not cube root, fourth root both sides. There you go. And here, just as a reminder, whenever you have a radical around a variable, your answer is always going to be plus minus, always plus minus. So, and the fourth root of 4096 is going to be 8. And there we go. So x is going to be equal to positive and negative 8. On example B here, we're going to do the exact same thing, but the first thing I want to do, get rid of that 9. And I'm going to do that by dividing both sides by 9. From here, rewrite that as a radical. And I'm going to switch this to 1 over x squared to get rid of that exponent as well, or that negative 1 exponent. From here, I'm going to take the fifth root, get rid of that fifth root by bringing that to the exponent 5 on the left and on the right there. So I'm left with 1 over x squared equaling to 1 over 59049, and of course from here squaring both sides, because x is going to be equal to each other, they're both in denominator, so x is going to be equal to plus minus again because you are square rooting just the x squared here, and again anytime you square root a variable it's always going to have plus minus, so this one ends up being plus minus 243. There we go. In this next example here, this is just asking us to use our graphing calculator to solve this. So method 1 is to use a y1, y2, and then find where they cross. Method 2 is to have everything as y1, and it doesn't mention here, but your y2 by default should be 0 because you have everything all in y1 now. You're going to find the solutions, and both of these should net us the same answer. Let's set up our graphing calculator. And here we go. On my graphing calculator, I've just set up my y1, y2. I'm ready to graph. Make sure that you have a standard window setting. There's my y1. There's y2. I'm going to go second trace option 5 to find where they cross, bringing our cursor to that intersection point. If you hit enter three times, there's our answer. We're really just concerned about the x value, not the y value, because there's no y's in our original equation. So our x value, or our solution there, is negative 3.1 if you really rounded. So I got x equals negative 0.31. There we go. And on the right side we're going to do the exact same thing, but this time with a 0 instead for y2. So on under y1 I just want to subtract off this equation. And a reminder that that subtraction is only in front of the 7 there, not, it doesn't change any of the variables there, and minus 3 there. And under y2 I'm going to put it 0, and again hit graph. And there we go, we have our graph going up. Again, second trace option 5, enter, 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 gets us to that same intersection point. Again, we don't really worry about our y values as we don't really need it. And all we're looking for is that x value, and of course it's the exact same for both there. So again, x is equal to negative 0.31 approximately there. In this next question here, we have the beginning of our word problems. So in most word problems, they'll give you an equation. In this first one, this is our compound interest equation. So where A is always the amount at the end of the investment, P is your principal amount or your initial, I is always your interest rate, and N is your number of compounding periods. Quick notes about I and N. So I, your interest rate, is always going to be a decimal. It can't ever be a percentage. So you always want a decimal, and it's going to be really uh, whatever your percentage or decimal. So I'm just going to write percent here, which you'll have to convert to a decimal. Is always going to be divided by your compounding period. So however many compounding periods you have, you want to divide it by that there. A quick note about n. And here says the number of compounding periods. Well, n is truly your number of compounding periods multiplied by time. So it's going to be time multiplied by compounding periods. So basically this tells you how many compounding periods do you have within a certain time amount, and so that's going to get you your total compounding periods. So here we go, we got this question here. Joseph wants to buy a new guitar. $2,700 is what it costs. He has $1,500 investing in a deposit that pays 7.5% per year, compounded quarterly. So there's going to be our compounding there, quarterly. How long does it take before Joseph can buy the guitar? So it says here, solve by graphing. Consider carefully what x represents. So let's set up our equation here. So our overall, what we want to end up with is 2,700. So that's going to be my A value. That's going to be equal to my initial 1,500. There we go. Brackets and brackets here we have 1 plus our interest rate, which is 7.5%, which is 0.075, because you can't have a percentage there, it's always a decimal, and you want to divide that by your compounding period. And so our compounding period is going to be quarterly, which means 4. So 4 times in a year is when you'll get this. Close bracket here, and our exponent is going to be n, which we don't know the amount of time is because that's what we are truly trying to find, but we have 4 for our compounding period n, so it's going to happen 4 times in that n or x amount there. So option 1, you can either type all this into your graphing calculator, y1, y2, and you'd have to play around with your window setting. So here we go. So under my graph here, I'm going to go y1 as that equation there, so 1500 brackets 1 plus, and if you can figure out your decimal here, great. If not, then I'd just set up a decimal on your calculator. 0.075 there for my percentage divided by 4. Close bracket, all of that to exponent of 4x, and x is our replacement for n, by the way. 2700 here. So what I want to do is change because if my y value is 2700, I definitely want to play around with my window setting. I want to bump it up to something at least higher than 2700. So I'm going to go up to 3000. That should cover it. And let's go up by something like 500. If you hit graph right away, here's what we get. There's our equation, and there's a line that goes through it. We need to find where they cross. Second trace, option 5. Moving our cursor closer to that intersection there, hit enter 3 times. 1, 2, 3. And there we have it. We have our answer. So x equals 7.91. That's what x is equal to. And of course, x was n there, n being our time. So x equals 7.91. And again, 7.91 is in terms of years. And so what you want to do is round to the nearest whole year. So n, truly, it should have been n equals 8 years. So it'll take approximately 8 years for this investment to reach at minimum $2,700. In this next example here, this is a growth and decay curve. Again, we're always going to try to cue you with the equation. So here's our equation: y equals AB T over P, where A is your initial amount, B is your growth and decay factor, T is always your time, and P is your time required for the growth and decay to occur. So write an exponential function for our carbon-14 here that has a half-life of 5730. So here I'm going to set up my equation y equals A. I have no idea how much carbon-14 I start off with, but I know I have a half-life, so that's our B value. That's my growth and decay factor, half. It's going to be to the exponent of T, our time, divided by P. We know that the half-life occurs every 5,730 years. That's going to be my initial equation. In part B here, we have a sample. This time we know our initial amount of 200. Sample of 200 carbon. How much carbon to the nearest hundredth, again, 2 decimals, will remain after 15,000 years. So that's going to be our time. So let's plug this all in. So we have y equals 200 bracket half. All of that is to the exponent of 15,000 over 5,070, or 5,730, that is. And all I'm going to do is type that into my graphing calculator, and I get 32.58 grams. On this part C, it's asking you what percentage, keyword percentage, will remain after this time period has passed. So again, we're going to probably start off with our initial amount because it doesn't tell us our initial. So let's start off with our 200. So y equals 200 for 1/2 of 12,000 this time. 12,000 over that 5730. So here, what's left over for our sample, we're left over with a sample of 46 point, and I'm going to use every decimal right now, 83, 82, 527 grams. That's what's left over. To figure out that percentage, all I do is take what's left over, the 46, 838 with all those decimals, divide that by our initial amount of 200 grams, multiply that by 100 to get to a decimal, of course, and that's going to get us to a decimal of 23.42%. So that's our percentage question. In example D here, how long will it take for the sample of carbon-14 to decay to 1/200ths of its original mass? So if A, my initial amount was 200, to get to 1/200ths of this, I'm going to go 1 over 200 multiplied by my initial amount of 200. So I want to find out when it gets to 1 overall. Therefore, our equation is going to say 1 equals 200 with our half-life 1/2. And we don't know how long that's going to take over 5730. There we go. And on this one here, you most likely want to set it up on your graphing calculator. If you type it in as this here, I'm going to tell you change your x values so that it's something big. I'm going to do a quick flip. I'm going to move this 200 to the left side here. So it's going to be 1 over 200 equals 1/2 n to the 5730. And sometimes when you do that, you're just working with smaller numbers. So here we go. So I have 1 over 200 on the left, and then I have that 1/2, which I can simply use 0.5 on my graphing calculator, to the exponent of x over 5730. Knowing that x is going to be divided by 5730, I'm going to change my window setting here. I probably don't need as such a large value for y there, so I'm going to go to 10 and 1. But for x's, I'm definitely going to need something bigger. I'm going to try something wild like 50,000 there. Let's go up by 10,000 there. Hit graph and let's see what we have. We have one line, we have two lines, and you kind of see that it's sloping down. Let's go second, trace option 5 there, and I believe they cross around here, but nope, they truly cross over here. So we have on our graphing calculator here, x equals, there we go. So let's scroll that down. So x or n equals there. And x and n is the same thing. So I got on my graphing calculator x equals the 43,799.296. And again, that's in terms of years, that's our time. So n in terms of time is going to take us, how long will it take? Let's round to the nearest whole. So that's going to be 43,000, well, if you have that one there, 43,800 years. There we go, to decay to this mass of 1 left over. For our final question here for today, example 6, again this is a growth and decay question, so we want to just fill in our equation. So our equation will always be y equals AB t divided by p there, if it's not given to us. So what's our initial amount? So y equals, our initial amount in 2012 is 10,777. That's our initial amount. What's our rate? We're decreasing it at 3%, so my rate is going to be decreasing, which is 1 minus 0.03. So that's how we're going to show decreasing, 1 minus 0.03. The time, we have no idea how often this is decreasing, but it's happening every year. So t divided by p every year meaning 1, we're going to divide it by 1. Let's clean this up really quickly. This is now y equals 10777 to 0.97 exponent t there. And here we're just going to put in 12 and 100 for part B here. So we got y equals 10777 0.97 to the exponent of 12, and that's going to net us a population of 7477.539. And of course, because this is a population question, we can't have decimals in our population. Round to the nearest whole. 7478 people remaining there after 12 years. After 100 years, how many people are remaining? So let's do the exact same equation, but instead this time we have 100 as our exponent, and y here is going to equal 512.47, and again, can't have decimal people, so let's round to the nearest whole. That's 513 people remaining in this population. The year that the population will reach 2,000 people, so we want to find the year, not how many years, but what actual year is it. So we're starting in 2012. In what year do we have 2,000 people? So let's set up our equation. So we got 2,000 people remaining out of a population initially of 10,777, with their decaying of 0.97 to the variable of n. And so, or sorry, I believe our variable should have been t for time actually. And so we do want to find t here, and the way that we're going to find this is use our graphing calculator. So again, I'm going to go y1, y2 on my graphing calculator. Here we go. So my y1 is going to be 2000, my y2, and again, again, if I want to, I can move that 10,777 over to where y1 is, or I can just leave it alone. Totally up to you how you want to do this. 0.97 exponent n, which is going to be x here. Right now, I know that this question, we don't need that big of a number, so I'm going to go as high as, let's say, 100 there. Let's go up by 10, seems a bit more reasonable. Let's hit graph and see what we get. So we have, oh, and of course we don't have enough y's, so let's go up to a y max. So we're hovering around 2,000, so let's go something a bit higher than 2,000. So I'm going to go with 3,000 and go up by 1,000, or even you can go up by 100 or 500, kind of whatever you want there. I'm going to go up by, let's say, 500. There we go. So there's my y1, y2. I find that they cross second trace, option 5 there. Enter, enter, enter. We're crossing at 55.29. So that's going to be our answer. So in this question here, so we got t equals, or basically x equals right now 55.295. So the time that it's going to take is about 56 years. But this question is asking in what year, so we're going to go 2012 plus the 56 years after, and in the year 2068, that's when our population is going to hit 2,000. Right, so that's the end of today's lesson. If you have any questions, please feel free to ask.